So we're here at the Markforged Technology Day at HK3D. It's been a great day, great turnout.
Yeah, absolutely. Yeah, really good. People from all over different industries. It shows that the interest in the technologies and the new products is really growing. I think.
And what is the technology?
So the core offering for Markforged is an FDM-based plastic printing technology that enables you to lay continuous fibre reinforcements within your parts. So that includes carbon fibre, Kevlar, fiberglass materials, and essentially enables you to build and create incredibly strong, rigid parts using what is essentially a very traditional FDM process.
So maybe not just fit and function, maybe end-user parts?
Absolutely, yeah. So this increased strength and abrasion resistance, those kind of qualities, really make these parts usable, in end-use applications and environments.
And what are the printers on show today?
So we've got the Mark II Enterprise, which is the top level of that particular form factor for the Markforged machines. That will run all of the fibre reinforcement materials and the nylon plastic materials as well. There are some other lower level models that will have restrictions on the types of fibres you can run in them, but essentially the same build volume enabling there. We've also got a Mark X machine, which has a bigger build volume. It also has a laser micrometer attached to it, so we'll do scanning up to a 1 micron accuracy. And then we've also been talking about the new Metal X products that we're expecting to be launched in September of this year, which is a MIM type technology, but essentially using an FDM layout process.
Yeah, and that's what excites me as an engineer. The metal, the plastic's one thing, carbon fibres, but the metal technology. And you've also you're making it affordable to pretty much every engineer or design house, aren't you?
Yeah, absolutely. So, so really what it enables you to do in terms of the environmental kind of aspects of it, the infrastructure required to run it. We have additive manufacturing powder technologies here, metal laser powder technologies. They need to be fully closed off. They need to be fully installed in a certain way and kept separately. These machines you can run in an office environment, essentially because the metal powder is encased in a plastic polymer that's basically then run into the part as you would expect with an FDM, like with the FDM technologies that Markforged are currently running. It's then debound, similar to MIM technologies, and then sintered down to its final state.
Yes, if I'm a UK SME or maybe an OEM, it doesn't matter. Why am I going to buy this metal technology?
Because it provides access to metal printing. I mean, so the cost that we would kind of put onto a 100 by 100 cube for a standard laser machine, the machine itself would be around the 200k mark, plus the infrastructure, plus all of the other consumables and it's an expensive process, an involved process. This machine will basically comes as a kit for 105k all in, and will enable you to print near net shape metal parts, end-use metal parts, basically from that point, with a build volume of roughly 200 mil cubed.
Okay, and a lot of these 3D printers from other manufacturers, you have to look at third-party software, don't you? Whereas it's all kind of in the package here, isn't it?
Absolutely, yeah. It's all part of the Markforged philosophy and workspace environment. So all of the printers use the same software, which is cloud-based, browser-based software, and so you get the same functionality. So perhaps you've been running Markforged plastic printers already, you're used to that environment. The Metal X, the metal printer, will run in the same environment with some additional functionality when it's released.
And I've had a short demo of the software. It's incredibly easy to use, isn't it?
Yeah, it is really, really simple to use. The technology itself is quite groundbreaking, quite disruptive in terms of the additive manufacturing environment. Being able to put continuous fibre within parts, is quite a step forward. But the actual interface is very intuitive. Obviously, there's depth there, so the more you get into it and the more you control you want over your parts, you're able to do that. But essentially, green button printing is simple, so being able to put parts onto your build plate and get them out of the machine itself is a very simple process. And the same will be for the Metal X, which again is a massive change. We're used to long lead times, long preparation for machines, especially preparing a machine for a print in a powder-based, laser-based technology can take up to a day. This will be very, very representative of the existing FDM technologies, so a matter of minutes essentially.
Yeah, the other point I like about the metal is the changeover times. I know the rollout, we're going to have more than around a dozen materials. It no longer takes 2 days to change a machine over, does it?
No, that's right. So at launch, the 17.4 and stainless steel will be launched as a base material. There are additional materials that will come as well. But those materials essentially are in rod form. We're expecting within a cartridge-based feed mechanism. So essentially, when you want to change it across, literally lift that cartridge out, replace it with a new material. Obviously, the sintering parameters will change on each material, but it's as simple as that. Obviously, again, that's a big change from what we're used to with powder-based systems.
So if we look at these brake levers, I'm presuming they're all different materials but the same component?
Yeah, that's right. So this really gives you an indication of the types of materials that are available and I guess their usefulness in different applications. So it's a simple brake lever. I think this is actually off a Ducati. Here we have it printed in a 50% infill, triangular infill with the nylon material. Obviously, it's not going to be too useful as a brake lever itself, but it shows the properties of that particular material. What we have following on from that is the same nylon base plastic material. This time we have continuous fiberglass reinforcement throughout the part. So what we're doing is we're adding strength, rigidity to the part, and we're starting to see that actually that could be a prototype, it could be something that we can use for practical testing, and possibly even end use depending on the application of it. And finally, from the plastic side of things, we've got the onyx material. So onyx material is still a nylon-based plastic material that has chopped fibers strands within it, random orientated strands. This is that material plus carbon fiber reinforcement throughout, so continuous fiber reinforcement. So that's as strong as a part you can get really from any FDM technology.
How would that compare to aluminium?
Yeah, so very favourably, yeah. So we can see that that essentially stands up against aluminium in terms of strength and load testing and those kind of things. So yeah, it's very, very strong and durable. Finally, a different style of brake lever. This is a sample part from the Metal X machine. So again, the same process. It's still layering it layer by layer in an FDM style. What it's doing is it's being able to do that because the powder material, the metal 17.4, is being laid down within a plastic binder. What we then do is debind that in a wash system after the printing process and then sinter it. The sintering process reduces the size by about 20% and removes all of the plastic polymer, leaving only the metal itself, which again is absolutely comparable to kind of bar stock 17.4 stainless steel. It also allows us to embed internal geometries within the part and within the shape itself. If we were to do that, we could do that with a powder-based system, but what it would do is encapsulate the powder within the part. So we would not really be making any weight saving. We wouldn't be laser sintering those particular areas, but it wouldn't really help us. Whereas with this, we actually save weight, and we produce a part that we couldn't produce with any other technology in any other way.